Hello, so in today's video, we're going to focus on something called Pascal's triangle. So you may have seen this triangle before. It's just a triangle of numbers like this here. So the way this works is that you start with the number one up there. You're going to put the number one here and the number one here as well. And then what you basically do is you add the two numbers together there to get this middle number down here, which is 2. So 1 plus 1 is 2, so you get 2 there. And you put ones either side of it. Again, you put ones at the end there, so 1 at the end here, 1 at the end there. And then 1 plus 2 will give you 3, so you get a 3 there. And then 1 plus 2 again there gives you a 3, so you get a 3 there. So you see the pattern. 1 plus 3 gives you the 4 there. 3 plus 3 gives you the 6 there. 3 plus 1 gives you 4 there. So the two numbers above a number, when you add those together, you get that number. That's how Pascal's triangle works. So why is this useful? I mean, we'll come on to why this is going to be useful in the A-level pure maths course in the next video, but we're just going to today focus on some of the meaning behind the numbers that we get in this triangle here. So firstly, let's just go through some notation. So when we've got this triangle like this, the way we call the columns and the rows is not like conventionally how you call like a column a horizontal line and a row a horizontal line and a column a straight vertical line. So the rows, I mean, are the same. So this would be called row 0. So your top row is always called row 0. Your second row here is actually called row 1. Your third row is called row 2. And then your fourth row 3 and row 4. So that's how you name the rows. And in terms of the columns are actually these diagonals here. So column 0 is this diagonal going on forever down there. So that's your 0 column. Then your first column is actually this column down here. Your second column is this one down here. Your third column is this one down here going forever and forever. And then your fourth column is this one here. If I actually just put in the next numbers in Pascal's triangle, so this would be a 1 there. 1 plus 4 would give you a 5, so you get a 5 in column number 1. But row 5, this is now row 5. For column number 2, 4 plus 6 gives you 10, so we get a 10 in there. Then again, 6 plus 4 is 10, so we get a 10 in there for column number 3. 4 plus 5, 4 plus 1 is 5. And then 1 is going to go here, and that's going to be in our column number 6. So we now add an extra column. This becomes column number 6. So that's kind of how we name the columns and the rows in Pascal's triangle. That's just the notation for what we use. Now, going on to some further notation. So how do we actually code or write some like actual notation for like the numbers in Pascal's triangle? So the way we do this, there's two ways that you'll see how we do this, and different people use different ones. They both mean exactly the same thing. So you may see like this kind of quote vector notation. So NR. So if you ever see this NR, then this is the number in Pascal's triangle. So it's a number in this triangle on the nth row and the rth column. So row n and column r. Or you could also see this notation here, nCr. Again, we'll come on to why there's a C there in a minute. But nCr is another notation that you could use to write this. So again, the nth row, the rth column. So the number that is in row n in our triangle and column number r in our triangle would be this number here. So actually, let's look at some examples to help out. So what would be 0, 0? So in other words, what would be 0C0? What would be that value? So it's going to be row 0. I'll write the answers over here. So row 0, which is this row here, this is row 0. I'll just use R0 for row 0. And then the columns of these diagonals here. So column 0 would be this diagonal column of 1s. So actually, this means that 0, 0 must be equal to the number 1 because it's the 0 row, the 0 column. That number that we've got in Pascal's triangle is 0. Okay, so that's the first example. How about example number 2? So what is 3, 2? So what is 3C2? What number is that in Pascal's triangle? So we're going to go to row 3. Okay, that's row 0. This is row 1. This is row 2. This is row 3. So this row here, this fourth row is actually called row 4. and we want column 2. Okay, right. So again, this diagonal of 1s is column 0. This would be column 1 here. 1, 2, 3, 4, 5, 6. 1, 3, 6, 10, 15 would be column 2. But 1, 4, 10, 20, this would be column number 3. So we want column number 2, don't we? 3, choose 2, or 3C2, 3, and then the 2 in the vector there. So we want column number 2. This is our column number 2, this one here. So we want row 4, column 2. So go across in row 4, column number 2, this number there. So 3, 2, or 3C2 would be equal to the number 3, because we can just read off from Pascal's triangle there. And then our next example, so what is 6 and 4? So 6C4, and it's what I said before about a minute ago. C stands for the word choose, and again, we'll come on to why we use the C for the word choose, as in choosing something. We'll see that in a minute. But okay, so we want row number 6. Well, that's row 4 there. This must be row 5. This is row 6 here. Okay, so row 6 is this number here. This row number's here. So that's row 6. And we want column number 4. Well, that's column 0. That's column 1. Sorry, column 2. This is column 3, 1, 4, 10, 20. Column 4 would be this one here, 1, 5, 15. So this is column number 4. We want row 6, column 4. So we're going to go across to here, down to there. It's going to be that number there. So it's going to be so 6 C4, or 6 choose 4, or 6 over 4. That's going to give us the number 5. Okay, so that's how we can use this notation to read from Pascal's triangle. So that's just what the notation means. And again, there's 2 ways in which we can write this notation. Now let's actually think about the real meaning, or the real applied meaning behind the numbers in Pascal's triangle, because there's actually quite an interesting meaning behind these numbers. They're not just random numbers that you add up in a triangle. They're actually numbers that are useful in like applied problems. So yeah, the nCr, or nR, is actually the number of ways in which you can choose R objects out of a total of N objects. So yeah, so interestingly, these numbers in Pascal's triangle actually tell you the number of ways, a number of different combinations. So that's kind of where this C comes from, combinations, choosing combinations. That's why you use this capital C, or why that notation was designed. So again, it's the number of ways in which you can choose. So this choose, again, this C notation. So you can choose R objects out of a total of N objects. So out of a total of N objects, how many ways can you choose R objects? And actually, these numbers in Pascal's triangle, funnily enough, tell you the number of ways. So if you want to know the number of ways that you can choose, for example, with this question 3 here, if you've got 6 objects, like 6 marbles, and you want to find out how many different combinations can I have to choose 4 of them. So if I want to choose 4 out of it, if I've got like a red marble, a blue marble, green, pink, yellow, brown, so 6 marbles, how many different ways could I choose 4 of those marbles? Well, it's actually going to be 5. So there's 5 ways in which we can choose the 4 out of 6 marbles, and Pascal's triangle actually tells us that. So let's look at like another example down here then. So if I have 7 different colored pens, so it could be red, blue, green, yellow, pink, brown, orange. So we've got 7 different colored pens. And I can take only 3 of them into an exam. So we've got 7 in total, but I'm only allowed to take 3 into the exam with me. How many different ways, how many different combinations could I choose these 3 pens? So, I mean, I could choose a red, yellow, brown, could choose red, yellow, blue, green, orange, yellow. There are different combinations of pens we could choose, but how many different combinations are there? So we can actually use Pascal's triangle to tell us. So again, this is going to be row 0, R0. This is going to be row 1. Row 2 would be that one there. Row 3 would be this one here. Row 4 down there. Row 5 there. Row 6 there. And row 7 there. So again, this diagonal there would be column 0, column 1, column 2, column 3, column 4, column 5, column 6, column 7, and so on and so on and so on. So we want to choose 7. So we've got 7 different colored pens. So our n value, our total number of objects, the n value in this case would be 7. So we want to choose 7. We've got 7 in total, and we want to choose 3. So the 3 would be this R there. That would be the 3, and the n would be the 7 there. So that's kind of how the notation's corresponding across. So we want to work out 7, 3. So row number 7. So again, this is the row, and this is the column. So 7, choose 3, 7C, 3. How many ways can we choose 3 objects out of 7? So we're going to go to row 7 and column 3. So column 0, column 1, column 2, column 3. So it's going to be 35. Okay, so Pascal's triangle tells us that the answer, so how many different colored pens can we choose for the exam if we're only allowed to choose 3 of them? There are 35 ways in which we could do that, and that's what Pascal's triangle tells us. So it's actually a very clever way in which we can basically get the answer to that question. But it's quite important, I think, in my opinion, to not just know that as a fact. I mean, that is a fact, but why does that work? So let's forget Pascal's triangle, and let's try and answer this question logically. I put that in speech marks. Let's try and think about this carefully. So if you have 7 pens and you want to pick 3 pens, how many ways can you do this? So sorry, let me just put like another box there. So these are boxes that we're going to put the pens into. So let's think about this first box here. So how many, so we've got 7 pens. How many different ways could we put 7 pens into the first box? Well, if you've got 7 pens, there are 7 ways in which you can do that. So there's 7 ways in which you can put a pen into the first box there. Okay, so we now put one of the pens into the first box. How many ways are there to put the rest of the pens in the second box? So we've already picked 1 pen. So again, we've got our 7 pens. We're going to pick 3 because we want to pick 3 pens. We've already picked our first one. So there's 7 ways we can pick our first one because we've got 7 different colors. How about our second one? If you've already picked the first one, how many ways do we have to pick the second one? Well, we've got 6 ways of doing that because we've got 6 colors left. So there are 6 ways in which we could pick the second. And then how about the third? How many ways could we pick the third pen? Well, again, we picked the first 2. We've got 5 left over. So there's 5 ways of doing this. So altogether, there are actually 7 times by 5 times by 6 ways of putting these 3 pens into this order here. So actually, if we just do 7 times by 6 times by 5, the number that would be, I believe, would be 210. So there are 210 ways of putting a pen into the first one, then the second one, and then another in the third one. So we want to times these together. And the reason why we times these together is because yeah, there are 7 ways in which we could put the first pen into the first box. So when we pick our second one, we want to times the remaining 6 pens that we have, because we've got 6 ways of doing the second pen. We want to times that by 7 because we want to make sure that every combination is accounted for. So all 7 pens matching with all 6 pens, 6 times 7, 7 times 6. And the same thing with here, we want to times the 5 there with the 5 left over pens in for the third choice. Okay, so there's 210 ways in which we can do this. Obviously, that's not the same answer we got here. We got 35. So why is that? And that's because the order does not matter. So, I mean, when we choose our pens back here for the exam, it doesn't matter whether we choose like the red pen first and then the blue and then the green, or the green first and then the red and then the blue. The order in which we choose our pens is irrelevant. So in this question here, when we did the logical thinking, the order did matter. I actually made the order matter because I said, how many ways can we pick the first pen to go there, the second pen to go there, the third to go there? So when we did this calculation, the order did matter. But really, in this real life example, it doesn't matter which order you pick the pens in. It doesn't matter whether you pick red, green, or blue first, or as I said, green, blue, red. The order is irrelevant. As long as we just pick 3 pens, that's all we care about. So the order doesn't matter. So it's irrelevant which pen comes first, second, third. We just want to choose 3 out of 7 pens. That's all we want to do. Okay, so how are we going to account for this then? So we need to divide the result we got. So we got 210. So 7 times 6 times 5, we got 210 ways, or 10, the correct word is 210 permutations. So when the order of your choosing, the order in which you pick things matters, it's called a permutation. But you don't need to know that for the A-level maths course anymore, but it's called a permutation. But the number of ways we can, so yeah, we need to divide 210 by the number of ways we can rearrange three objects, because again, when we choose our three pens, it's irrelevant whether we choose the red, green, or blue first. It's irrelevant as long as we choose the three pens. So we need to divide this number by the number of ways we can rearrange these three pens, because the order in which we pick them, again, doesn't matter. So how many ways can we rearrange three pens? So we've got 1, 2, 3 there. How many ways could we rearrange them? Well, the first pen could be, well, if we think about this, we got three pens. In order to decide, well, in order to think about the number of ways we could choose the first pen, again, there are three ways in which we could, out of our red, blue, green, there are three different like pens that could go first. It could be red, blue, green. So then again, in terms of our second pen, what could come next? Well, again, we've picked our first pen. Let's say it was red. So there's a blue pen, green pen left over. There are two different ways of picking the second pen. So two there. So two ways. And then our last one, we've got one pen left over. There's one way of picking that last pen because there's only one pen left. So 3 times 2 times 1, which is 6. There are actually 6 ways of rearranging three objects. So in other words, 3 times 2 times 1 is exactly the same as 3 factorial. So remember this factorial notation. I don't know, you may have seen it, you may not have seen it. So 3 factorial is just the same as 3 times 2 times 1. 4 factorial would be 4 times 3 times 2 times 1. 5 factorial would be 5 times 4 times 3 times 2 times 1. 6 would be 6 factorial will be 6 times 5 times 4 times 3 times 2 times 1. That's how factorials work. So when you want to rearrange three objects into order, there are 3 factorial ways of doing it. When you want to rearrange 100 objects, there would be 100 factorial ways of doing it. So this is always a fact. So when you want to rearrange n objects, there are n factorial ways of doing this. I'm just going to make a note of this down here. So there are n factorial ways of rearranging n objects into a particular order, n objects into a particular order. Okay, so that's the key point from there. Okay, so yeah, so going back to our question, we're choosing 3 pens out of 7. So that means, yeah, there are 210 permutations for doing the pens. So 7 ways of picking the first one, 6 ways picking second, 5 ways picking the third one. So we got 210 for that, but we got to divide it by the number of ways we can rearrange those 3 pens, because the order doesn't matter in which we choose the 3 pens. So we divide that by 6, and when we do 210 divided by 6, we do indeed get 35, and which was the same answer that we got back here using Pascal's triangle. So yeah, so it does work. So we get exactly the same way when we think about, sorry, the same answer when we think about it logically. Okay, so we get the same answer there. Now let's try and think about a formula. Let's try and think about how we could put this into some kind of algebraic formula. So if we go back to the numerator of our fraction up there, so we had 7 times 6 times 5 to get the number of permutations to get these pens. Okay, so hopefully you agree with me that 7 times 6 times 5 is the same as 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 4 times 3 times 2 times 1. Why would that be? Well, the 4 would cancel out there, the 3 cancels out there, the 2 cancels out there, the 1 cancels out there. So basically, just instead of writing 7 times 6 times 5, I'm just doing this kind of trick where I'm rewriting it in this order here. So in this fashion here. So okay, so what is this? So on the top, this is 7 factorial. And on the bottom, this is 4 factorial. Okay, so we got So the number of permutations, so again, this was our permutations. So permutations. So the number of permutations was 7 factorial over 4 factorial, but we wanted the number of combinations. So we had to divide our answer by this 3 factorial here, didn't we? So remember, this on the bottom was 3 factorial. Let's just make a note of this, that this was 3 factorial. So now we want to divide this fraction by 3 factorial. So 7 factorial over 4 factorial divided by 3 factorial. Well, that's just going to be 7 factorial over 3 factorial times by 4 factorial. So 7 3 in Pascal's triangle, or 7 choose 3, is the same as 7 factorial over 3 factorial times 4 factorial on the bottom. So how could we put this into an algebraic formula with n's and r's instead of just like normal numbers like 7 and 3? So remember, so our 7 was our total number, so that was like our r value, our n value, 3 was the number of objects we wanted to choose, so that was our r value. So in a formula, if we try and write this in a formula, so 7 was our n, so we would have on top of our formula, comparing the letters with these numbers here, we're going to have n factorial divided by the r factorial, which was the 3 here. So this would be the r factorial here. So r factorial, and then 4. Well, 4 is the same as 7 take away 3. 4 equals 7 take away 3. So 7 is the n, 3 is the r. So this is actually going to be n minus r factorial, and this is the formula for Pascal's triangle. So this is the formula for choosing r objects out of a total possible of n objects. So that is our formula. So in summary then, n over r, or n choose r, they're exactly the same, same notation. This is the same as n factorial divided by r factorial times by n minus r factorial. So just like a brief example then, let's say you wanted to find the number 10, 8 on Pascal's triangle. Instead of writing out Pascal's triangle for ages and for ages and for ages, looking at the rows, you can just use this formula. So 10 choose 8, that's going to give you 10 factorial on the top. The r would be the 8 in this case, so an r factorial there. And then n take away r, so remember the n in this case is 10, the r in this case is 8. 10 take away 8, that's going to be a 2 factorial. So 2 factorial there. I don't really need the brackets here, actually. So we're going to get, so 10 factorial divided by 8 factorial. Well, all the 8s, the 7s, the 6s, the 5s, 4s, 3, 2, 1s, they will all cancel out. So what we're going to get on the top is 10 times 9 divided by 2 factorial, which is 10 times 1. And again, that's because, let's just make a note of this down here, just to be really, really clear. So 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, divided by this 8 factorial, 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, and then times by this 2 factorial over here. The 1s cancel out, 2s cancel out, 3s, 4s, 5s, 6s, 7s, and 8s. So that's why we get the 9 times 2 on the top there. That's just by cancelling that out. And then divide by the 2 factorial. So 10 times 9, 90, divided by 2, we're going to get 45. So if you've got 10 pens, and you can bring 8 of them into the exam, there are 45 ways of doing that. Or if you've got like 10 different colored marbles, you're going to pick 8 of them to bring with you on holiday. There are 45 ways in which you could do that. And that is exactly the same number on Pascal's triangle as when you go to row number 10. So row number 10 on Pascal's triangle, if you kept on drawing it, and column number 8. So that would be the number you get there. It would be 45 in this case there. So yeah, that's just an example of how we can use Pascal's triangle, and also the n choose r formula, which is n factorial over r factorial times n minus r factorial. That's just how we can do those calculations. Now, you're not in the A-level UK maths course, you won't get questions like this in the pure math syllabus, But in the next video, we're going to see why this, like what the point of this is in the context of actually algebraic expansion and expanding brackets. We're going to see where this comes in handy, and we'll find out that this is actually quite a useful thing when we expand algebraic brackets, and we'll see that in the next video.